Alrighty, welcome back. Today we're going to be going over some stuff in 14K, looking particularly at the Pythagorean identity and some symmetries of pi on 2 between sine and cosine. So firstly, let's just remind ourselves of what the Pythagorean identity actually is. Now, as the name sort of suggests, it involves Pythagoras' theorem. So what we're going to do is we are going to draw a triangle, okay? Triangle like this, with an angle of theta, okay, extends down, and it's a right angle triangle. Now, because this is the unit circle, we know that we can label the sides, right? We can label the sides with side lengths of cos theta, because it's the x value, so that distance, and we can label this as sine theta. And now, hopefully you can see that Pythagoras' theorem is actually really easy here. We can simply just say that sine theta squared plus cos theta squared is equal to 1. Well, it's equal to 1 squared, but that's equal to 1 as well. Just as a little bit of notation, sine squared theta is equal to sine of theta squared, just so that we don't accidentally mix up theta getting squared or the whole thing getting squared. Now, a natural question one might ask is, Mr. Lung, what happens if this angle isn't in the first quadrant? What happens if it's somewhere else? And that's a very fair question. But what I would like to say is, I would like to say that any other angle, you can always draw a triangle that gives you one of these in the first quadrant because of symmetry, right? So for example, let's just take this triangle down here. Okay, and let's say that it goes around, it has an angle of theta, so it's going to be an angle of pi plus theta. Okay, now obviously theta can be anything, so this could refer to any angle. And now we just use our definitions again. We know that this is going to be negative cos theta, and this is going to be negative sine theta. Fair enough? But we can see that it still holds, because when we square these side lengths, those negatives go away, right? So if we have, for example, negative sine squared, or sorry, negative sine theta, and we square it, it's just going to equal sine squared theta. And same thing with negative cos theta. If we square it, it's just going to equal cos squared theta, because the negatives will cancel out. So we can see that this Pythagorean identity holds for any theta in the unit circle. Cool. So that's really awesome. It means that if you have the value of sine theta or cos theta, you can find the other one, because you can just rearrange this identity. Cool. Okay, so let's also have a look at some symmetries of pi on 2. So when we say symmetries of pi on 2, what we mean is what happens when pi on 2 is offsetting our angle. So again, let's draw two triangles here, but we'll draw them in different colors. So firstly, let's draw a triangle like this. We'll label this angle here theta. Okay? Boom, right angle. Now, we want to investigate what happens if we take this angle, but instead of moving it around further than pi on 2, what happens if we actually just take pi on 2, that is a quarter rotation or 90 degrees, and we actually subtract theta instead, right? So we're looking at what happens with sine of pi on 2 minus theta, okay? Now the sine is measuring the y value, right? This is y value, okay? And the y value is represented, and I'm going to draw these in the same color very deliberately. It's represented by this, okay? That's that distance. That's sine of pi minus 2. Oh, sorry, pi on 2 minus theta. Okay? But these two triangles, are the same. They're the same because they have the same side lengths. Or, well, actually, okay. They're the same because of angle, angle, side, if you remember your congruence proofs. But that's not super important. What we just need to understand is that they are the same triangle, which means their side lengths are the same, which means these long side lengths are going to be the same, these green ones. And what is the length of that second green line? Well, this is actually just equal to cos of theta. right? It's the x value, or that distance, which means we can say sine of pi on 2 minus theta is just equal to cos theta. And very similarly, in a very similar way, we can say that the cos of pi minus 2, I keep saying pi minus 2, pi over 2 minus theta is equal to sine theta. That's pretty cool, right? That is, sine and cosine are just offset by pi on 2, which is pretty awesome. Okay, so we're going to use these. Let's use the identities first. So this is the symmetries that we just talked about. We're doing example 1, 14K, question 1J. If sine of x, that is an angle x, equals 0.3, find the cosine of 3 pi on 2 minus x. So we're going to use some symmetry, but first let's draw the triangle. We don't know what x is, but we know that the value, or the y value, is about 0.3. So let's put it about here. Okay, and we'll draw a triangle like this. And this angle here is x. Okay? Now, we want the cos of 3 pi on 2 minus x. So 3 pi on 2 is pointing directly downwards. Then we're going to subtract x. So it's going to look like this. And now, hopefully, we can see our symmetries at play again. We're using this idea that these triangles are the same. So firstly, before I do anything, I'm going to notice which side lengths are actually the same. That is, the sine value, the short side, okay, is 0.3. Okay? But because these triangles are the same, we can also say that this side here is 0.3. And that side exactly gives us the cosine value. So we can say, because short sides are the same, okay, we can use symmetry. And then we just have to notice one more thing, that cos of 3 pi over 2 minus x is negative, right? Because it's in the third quadrant. So yes, the side length is going to be the same. The short sides are both going to be 0.3, but cosine is negative here. So we can say, so cos of 3 pi over 2 minus x is equal to negative 0.3. And we're done. Yay. Okay, example 2, 14K, question 2D. Given that given that theta is in between 0 and 2 pi, which means that we are in the first quadrant, always label things like this, just makes your life a bit easier. And sine of theta equals cos of 3 pi on 7, find theta. Okay, so we know that theta is in the first quadrant, and we know that the sine of theta is equal to the cos of 3 pi over 7, okay, which is important. So, firstly, we recognize something important. We recognize that if we do a 3 pi on 7 angle, let's draw it in blue. Three pi over 7. Okay, we know that this is, well, the cosine value, or in other words, the long side, okay? And we want the sine that gives us the same thing, okay? So, how are we going to do this? Well, we're going to draw in a triangle, and we need to figure out what is the actual value of the angle that gives us the same long side. So, we know that it has to be in the first quadrant, right? Which means that the angle can't go past 2 pi. So our triangle has got to be somewhere like this. Okay? With this angle here as theta. Right? But we've got something really important. This identity, or this equality, gives us the fact that the cos of 3 pi on 7, that is the long side, okay, this is cos 3 pi on 7, is equal to the sine of theta, which is equal to the height. These two things have to be the same. Okay, and if they have to be the same, it means that the angles also have to be the same. Okay, which means that we can label this angle in here as 3 pi over 7. Okay, which means that we can simply say, well, maybe not simply, but we can say, in order for sine of theta to be equal to cos of 3 pi on 7, that is for the long sides, this is the long sides the same, okay, we need that theta is going to be equal to pi on 2 minus 3 pi on 7. Okay, we know this because it has to be in the first quadrant, so it can't be anything bigger than that. So now we just do some simplification. We say this is 14 pi on 7 minus 3 pi on 7. Okay, which gets us to 11 pi over 7. Now that doesn't look right because it's bigger than pi, so I've made a numerical error somewhere. Oops, no. That's wrong. So even your teachers make mistakes sometimes. We need to put them on a denominator of 14. So it's going to be 7 pi over 14. And we're going to multiply this one by 2. 14, 6. Great. Which means that it's equal to pi on 14. So the triangles actually will be quite a bit smaller. Did I do that right? Yeah, pi on 14. Great. Okay. So that's how we would use symmetries, but we're kind of using it backwards a little bit, right? We're using it a little bit backwards. Sorry, my laptop's just being a bit annoying. Okay, so let's move on to example 3 down here, which is question 5 in that same chapter. So given that cos of x equals 1 over 5 and x is in between 3 pi on 2 and 2 pi, find sine x and tan x. So this is an example of where we're going to be using the Pythagorean identity. Okay? The Pythagorean identity. So what we're going to do is we know that cos x is 1 over 5, and we know that it's in between these two things. So firstly, we just plug it into the Pythagorean identity. And we say, let's do it in pink, Pythagorean identity, it will give us sine x, and then we can use that to find tan x. So we know that sine squared of x and theta can be the same thing, cos squared of x is equal to 1, okay? Which means that we know that sine squared x plus 1 over 5 squared is going to be equal to 1. And now we just do a bit of algebra, basically. So sine squared of x is equal to 1 minus 1 over 25. I just squared the fraction, I subtracted it, which means that sine squared x is equal to 24 over 25. Okay. And then sine x is equal to the square root of 24 over 5. Now, we know that x has to be in between these things here, right? Which means that we need to figure out, is this positive or negative? Right? Because when we took the square root, we could have taken a plus or a minus, But we know that because we're in the fourth quadrant, okay, we know it's going to be negative. Okay, so we have to put a negative here. Great. So we know that's the value of sine x. Now, we can do a bit of simplification. I'll do it because your book has the answers in this way, so we don't get confused. Sine x, we just simplify the surd, is going to be equal to negative 2 root 6 over 5. Cool. So that's sine x. And then we'll do tan x. Tan x is just sine x over cos x, right? Tan x is equal to sine x over cos x, which is equal to, well, we know what sine x is, negative 2 root 6 over 5 divided by cos x was 1 over 5, I think. Yep, great. Which means that we get, if we remember KFC, flip our fractions, we get negative 2 root 6 times 5 over 1 times 5, which is just equal to negative 2 root 6. Which makes sense because we're in the fourth quadrant. So it makes sense. Tan is negative in fourth quadrant. And we're done. Yay. Cool. So those are a couple of examples from the textbook about how to use the Pythagorean identity and some symmetries of pi on 2. The unit circle is so beautiful because it's got these symmetries and because we can use Pythagoras' theorem. So it's really helpful to be able to do these to find some exact values for some things when we're given other pieces of information. Hopefully your own practice goes well. Have fun.